Thank you for watching another or clicking on another video of the Kaggle Top Solution series. If you haven't watched already, there are a few other videos where I explain top solutions by the grandmasters at h2o.ai. In this series, in under 10 minutes, you'll learn about the top approaches to many competitions across different problem sets. In this video, you'll learn about Qishen Ha, who's currently ranked in top 4 worldwide across the competition's leaderboard. How did his team finish in the top 5 in a competition? You actually have to scroll a bit on his profile because he's finished in top 3 so many times. We'll be talking about the UW-Madison GI Tract image segmentation competition. I had the chance to interview Chishan about this. It's an hour-long interview. Welcome to watch that. In this video, I'll try to explain his solution in a shorter form. So the goal of this competition is to help segment gastrointestinal cancer better. Obviously, it's an image-based medical problem. The challenge involves working with a lot of MRI scans across different days. So if I look over the data here, you can see inside the train folder, there are many cases along with scans across different days. The reason for that being across every single day, a cancer inside the intestinal tract can move ever so slightly, and you need to find the exact location to be able to apply the correct X ray therapy there or the correct treatment there. And as I mentioned, Chishan's team finished fifth, so we'll be learning about their solution. They'd use something known as a 3D CNN. What are those and how do they work exactly? I'll be using a tool that he created. I'll be using a feature from Hydrogen Torch, which is a no code deep learning tool. Chishan, after finishing really high on the leaderboard, added this feature to Hydrogen Torch so that you can also work with medical images. Let's check that out. Here I've loaded up just one dataset, which comes from Kaggle user LARXCL. So thank you for that. These contain lung scans of different patients. You can read more about it on this link. I didn't load the competitions dataset because it was quite large. So I've loaded this dataset up, and as you can see, it comes with all these masks across different images, and it basically consists of lung scans. I pre-processed it ever so slightly and resized them to a smaller image so that I can run this fairly quickly. Hydrogen Torch allows me to do a quick check where I can look at the dataset, and as you can see, the lungs are almost perfectly masked, and it helps me identify that using a simple visualization where I can hover my mouse and it shows me the label. I can do this for all the images, make sure, or this allows me to make sure that this has been loaded correctly. I can also take a look at the stats. So we're just working with 20 examples or so right now. What I'll do now is I'll create an experiment based on this. And I'm feeling quite adventurous, so I'll use the master setting. You can also set the setting to novice, where a lot of the settings are taken care of. But I'll set this to master, and from here I'll select from the dataset. I'll select image semantic segmentation 3D, which tells Hydrogen Torch that hey, we'll be working with a 3D image, and we'd like to use the 3D CNNs, please. This functionality is coming to Hydrogen Torch really soon, so you can find all the details and sign up for it in the first link in the description. Head over to the Hydrogen Torch page if you'd like to work with this. Now, what exactly are 3D CNNs? Usually, when you're working with images, those are 2D images and you have RGB channels. For 3D CNNs, you could have multiple channels. For example, in this competition, Kishan shared that he had used all of these 144 scans across every single day as a depth channel. So that is the third dimension. For this particular competition, the image size is 266 by 266, and there are 144 scans across every single day. That becomes the third channel, and that is what is fed into a 3D CNN. So that's how 3D CNNs essentially work. And we don't have to worry about setting up all the channels because this functionality now is coming to Hydrogen Torch. So what I've simply done, as I mentioned, is select image segmentation 3D, which gives a heads up that hey, we need 3D CNNs. I'll select a simple k-fold strategy, and we'll probably only train on one fold. I'll hover over the settings. I'd like to use the entire data set. Yes, please. Let's maybe resize this to 256 by 256, and if you have more compute hours to spare, you can also go all the way to 1024 by 1024. It's as simple as just moving the slider, as you can see. I leave the image channels to 1 and the image normalization strategy to simple, although you could have min max as well, and you could also play around with augmentation strategy, and you could enable or disable mix up if you'd like. And remember, all of this is working with 3D CNNs. I'll probably use a ResNet 101D here, and I'll leave the dropout to 0. You can also work with different decoder blocks, so you could work with unit plus plus or unit. I leave it to unit for now. I'll set the loss function as BCE dice, and if I want, I can also set differential learning rates across the encoder and decoder. I'll set the batch size to 8 because I'm working with 4 GPUs here. And this is one of the cool features I mentioned in the previous video. If you get an out of memory error, Hydrogen Torch won't crash the experiment. It will rerun with a smaller batch size. So I can enable that. And there is always a risk of an experiment not working properly in case the last batch has incomplete examples. So there's an option to drop the last batch as well, contrary to running the experiment and later finding out that you need to rerun it. You can just enable this and that will be taken care of. I'll probably set the slider to 50 epochs. I'll run it for the entire duration. And I can set the scheduler through here. We'll leave it at cosine because I found that works the best for most cases. So there are a few other options that I'm going to leave off here. And I'll set the metric as IOU. I don't need any test time augmentations, but if you want, you can use horizontal or vertical flips. I'll select all my GPUs and I'll use mixed precision training. We can set the number of workers to whatever the number of cores are on your machine. I'll set it to all 28 cores for my case, and I'll kick this experiment off. As it happens, I can monitor the progress right in the dashboard, and I can see the learning rate has been set to constant for now. I can monitor the train batch loss and a few other things. I can also take a look at the data inside. So it's predicting lungs here with confidence 1, and I can keep refreshing this as it makes its progress. I can also take a look at the validation prediction insights, which allows me to do a lot of things. So for example, I can make sure that the data is loaded up correctly, or it allows me to check if the model isn't working as expected. So if I look at the worst validation examples, I'll get the cases where the score is the worst or the model is struggling to perform. So that allows me to do a few things. And we got an IOU score of about 0.93, which I think is really good. This was across 4 GPUs, but the point I'm trying to make here is in about under 10 minutes, ideally, or under 15 minutes, you can run a lot of experiments and get a lot of feel about what backbone should you be working with, and you can get a lot of baselines that you can work off of. Let's see how Qishen use this approach or use these models to finish fifth along with his teammate in this competition. So he had said five-fold cross validation where he had a group splitting by case, and he had used something known as a 2.5D model. What is that? Normal 2D model is a resonant model where you load in a colorful image, a RGB image. In 2.5D, there are 5 channels being loaded into the model. So instead of RGB, you have 5 channels and you have data from, you could say, 5 different scans for this competition, or so on and so forth. I've already explained what 3D models are, so I'll continue from here. And he had also used some nice post processing. He says XYZ because if you can use or you can slice across different axes and arrive with different data. So that's how you derive the 2.5D model from a 3D sample. They'd use different libraries and they mention the same here. The famous TIM library, segmentation models, and also semantic segmentation. So they had constructed the dataset into 3D format. And then by cutting along the 3 axes separately, you can obtain 3 different types of 2.5D datasets, which are 2.5D X, Y, and Z, respectively. Then they trained 9 models where they basically use different architectures and backbones on different data sets. For 3D models, they had also used Mono AI. And they ended up using a ResNet unit on the 3D dataset along with an efficient net small and medium. For the final ensemble, they averaged the output of all models and used threshold zero point 0.3 to get the public leaderboard score of 0.889. They also did some post processing where they removed the false positives. So for those images where the predicted area was less than 50 pixels, they discarded them to get to their final score. So, quick overview and a quick summary of this fifth place solution. They use five-fold cross validation along with 2.5 in 3D models. They had constructed a data set to be able to work with 3D CNNs, and they applied some post processing to remove the false positives. And this is the fifth place solution of the Madison GI tract segmentation. Again, you can find the link to this write up as well as hydrogen torch in the description. Thanks for watching this video.